Good morning to one and all. Welcome you all to the Thermodynamics course. Myself, Arun Kumar K, Assistant Professor from Aeronautical Department, MLR Institute of Technology, Hyderabad. So in today's lecture, actually, we are going to discuss about Carnot cycle, or we can say the ideal heat engine. So in the previous lecture, we discussed about basics of heat engine and basics of heat pump or refrigerator, and we have solved the numerical problems based upon those topics also. So in the numerical problem, we have solved for performance parameters like efficiency and coefficient of performance. So we got the values, performance values, whether those values are feasible to construct the particular device or not, that we don't know, right? In order to sense that, right? So we supposed to have some theoretical values for the comparison purpose. So for that, actually, we have framed ideal cycles. That cycle is nothing but Carnot cycle. So for the heat engine, if it is reversed Carnot cycle, that is applicable for the heat pump or refrigerator. So with this, actually, I can able to compare the performance parameters so that I can able to conclude it is feasible to construct the particular thermodynamic device or not, right? Yes. So before entering into that, we will discuss about the Carnot principle. See, this Carnot principle is nothing but we have set the theoretical limits to the operation of all cyclic devices, right? So the heat engine, actually, we had the cyclic components, actually we had, and cyclic process we having, right? So with that, actually, we can able to set the theoretical limits also. See, the efficiency of an irreversible heat engine. What's that irreversible heat engine? That is nothing but actual case we are having, right? That is what the practical one we are having, is always less than that of a reversible engine. So what's that reversible is nothing but ideal one. So this is what the theoretical one, right? So this reversible is nothing but actually we call it as we can able to frame with respect to the Carnot, right? So this is what the comparison between the reversible heat engine as well as irreversible heat engine. Irreversible is nothing but always practical one or actual one, right? Actual one. And this reversible is nothing but actually we call it as ideal one. Over here it is nothing but the Carnot cycle, right? Efficiency of all reversible heat engine, ideal heat engine operating between the same reservoirs or the same, right? For example, if I am having TH equal to, right, 300 degrees Celsius and TL equal to, we are having as 20 degrees Celsius. For these two thermal reservoir, same reservoirs, right, the efficiencies of all reversible heat engine, if I am having multiple reversible heat engine, right, that reversible heat engine is operating between these two temperature, like reversible heat engine 1, reversible heat engine 2 and reversible heat engine 3, right? So these efficiencies will be remain same. That is what this statement says. So which means with respect to this, I can able to compare with the irreversible cases, right? So with that, actually, I can able to sense whether it is feasible to construct or not. So that is the basic purpose of this Carnot cycle we are having, right? So the Carnot cycle, actually, what are the points we are having? See, the cycle efficiency can be maximized by using reversible process. What is reversible processes? Ideal processes, right? So if I consider this ideal processes, then I can able to maximize. For ideal conditions only, we are having the maximum performance parameter, right? Or we can say efficiency, right? Instead of performance, we can able to say, we can sense with respect to the efficiency. So neat of ideal, right, is always greater than neat of actual. So that is a known case. So in order to get this ideal neta, I supposed to frame the reversible processes. That is what the ideal process I need to frame. Reversible cycles can't be achieved in practice because of the irreversibilities. In actual cases, right, irreversibilities are there due to many factors we are having. So because of that, we can't able to achieve with respect to the reversible cycles. That is what the ideal one. Reference one, we can't able to, theoretical one, we can't able to achieve it. And reversible cycles provide upper limits on the performance of real cycles, right? Upper limits in the sense, for example, in the actual cases, if I got neta of actual equal to 60% and neta of ideal equal to, right, 80%. So this provides the upper cases. So up to 80%, even we can't able to reach as 80%, towards 60 to 80%, right? We can able to improve the actual things, right? If I got only NEET of actual as 40% and NEET of ideal as 80%, what happened? The 40% difference actually we are having. So up to that actually we can able to maximize that. So for this comparisons actually we can able to have this Carnot cycle and it can able to set the upper limits on the real cycles, right? What is real? Real is actual, right? So it is proposed in the year 1824 by Sadi Carnot and it is a reversible cycle also. So Carnot cycle is nothing but an ideal cycle heat engine, right? And it is a reversible heat engine. So like that actually we can able to frame, right? Wherever reversible, ideal, this Carnot, right, mentioned, that is what actually we call it as ideal conditions we are having, right? See, the theoretical heat engine that operates on the Carnot cycle is called the Carnot heat engine, right? The theoretical heat engine. What is a theoretical heat engine? Reversible heat engine that operates on the Carnot cycle, right? Carnot cycle in the sense we are having the cyclic processes over there, right? Then we can able to say that engine is nothing but Carnot heat engine. So the reversible heat engine I can able to say, Carnot heat engine I can able to say, or ideal heat engine I can able to say. That is what the statement given, right? Right. Now, what are the various processes actually we are having with respect to this Carnot cycle, right? So the Carnot cycle consists of 4 reversible processes, right? So with respect to that, in general heat engine, what are the processes actually we are having? Suction and compression, right? And after that we are having compression. After compression we are having combustion, right? And after that we are having expansion, and then actually we are having exhaust also, right? So these are the 4 actual processes we are having. In general we have considered. So for that actually we have framed 4 reversible processes also. So what are they actually? 2 reversible adiabatic processes and 2 reversible isothermal processes, right? So reversible adiabatic is nothing but actually we call it as isentropic process, right? And 2 reversible isothermal process. So here actually the temperature remains constant. So these are all in the first unit. In the quasi-static process itself we discussed already. So the temperature remains constant throughout the process, right? And here actually reversible adiabatic is nothing but isentropic process where the heat transfer, right, between the system and surrounding is remains nil, 0, right? So in that way actually we are supposed to consider. So in order to frame this actually, it is executed in a closed system at a steady flow mode, right? So that is what we discussed in the unit 1. And we shall consider a closed system consisting of a piston cylinder arrangement. For a heat engine, simple heat engine, we'll consider the piston cylinder arrangement. So for that, what are the various processes actually we are having, that we'll frame right now, right? See, friction and other irreversibilities are assumed to be absent. So this is what actually ideal. See, for ideal cases, always we supposed to consider it is nothing but frictionless, right? And other irreversibilities also we are assuming that to be absent. So which means it is comes under reversible conditions, right? So the friction losses and these things and all no need to consider with respect to the Carnot cycle, right? Now we'll start with the first process, right? So we'll start with respect to the power stroke actually. So which is a major purpose of what is the objective of heat engine actually we are having? The work extract from the thermal energy or heat energy, right? So that actually happens with respect to the expansion process we are having, right? So there actually they have started with respect to this reversible isothermal expansion. So I'm going to consider, right? So after this, see, I'm having the piston cylinder arrangement. Expansion is nothing but the volume get increases, right? And the pressure get decreases. But for the maximum case, how to assume is nothing but if I assume the temperature remains constant throughout the process, right? So that is what the isothermal expansion we are having, right? So reversible isothermal expansion, if this process carries, right, then we can able to say this is what actually the ideal expansion process we are having. So as we discussed, compression, combustion, expansion, exhaust, right? That is what heat rejection. So everything we have discussed. So for that expansion, I suppose to consider reversible isothermal expansion. So if I consider in this way, then only I can able to get the maximum efficiency. Which way? Isothermal. If I maintain the temperature as constant until the completion of this expansion process, then I can able to get the maximum efficiency, right? In that way I have assumed actually, right? And see, gas allowed to expand slowly, right? What is that? A reversible isothermal expansion we have assumed actually. Listen here. So we are having gas allowed to expand very slowly, right? And infinite smell, heat transfer to keep THS constant, right? So infinitely slow manner the heat transfer takes place, so that I can able to assume the temperature remains constant. What is the temperature remains constant? Where the actually we are getting that energy actually from the source, reservoir. What is that source reservoir actually I am having? The source reservoir is nothing but actually I am having as with respect to the TH, right? I can able to maintain this as a TH. Since the temperature differential never exceeds del T, the reversible isothermal process, right? Since the temperature differential never exceeds del T in the sense we are having the delta T we are having, right? So with respect to that, it never exceeds. So the reversible isothermal process I can able to assume it, right? The total heat transfer is nothing but from the QH. That is what we are having with respect to the source, right? Yes. Next process is nothing but actually we are having reversible adiabatic expansion process. See, listen here. So that is what the power stroke I said, right? That's what the power stroke, the combustion stroke I said. And after that, see the reversible adiabatic expansion. See, listen here. In the 1-2 process I said. So there actually we have started the TD, the piston head with respect to the top dead center, right? This is what the position 1. So 1-2 that power stroke. What is that actually power stroke? We have added the combustion. That is what the QH we said, right? So we have added the thermal energy to the working substance. Assume that inside we are having that working substance inside this. So this get, right, the energy get added in which way actually? Through the expansion process. So up to this 2 point actually, point number 2. What is this point number 2 actually we are having? This is the in between the TDC and we are having BDC. In between TDC and BDC. So in between that actually up to this we have added the power, right, through that reservoir, source reservoir, right? And after that 2 to 3 is nothing but actually 2 to 3 is nothing but here we are having the adiabatic expansion. So once the power addition is completed, then automatically it pushes the piston down, right? So because of that actually the reversible adiabatic expansion is nothing but without transferring energy to the surrounding, right, through these boundaries Q equal to 0, right? So this is what actually we call it as process number 2 to 3. So in process 1 to 2 is nothing but TDC to in between TDC and BDC it reaches point number 2, and 2 to 3 is nothing but 3 point is nothing but at the end of this adiabatic expansion, reversible adiabatic expansion process, it reaches the BDC, bottom dead center, it reaches piston, right? So see, assume this is well insulated. That is why actually we can able to assume as Q equal to 0, right? But in actual cases it might be not well insulated, but even though well insulated, we are having some amount of heat is transferred to the surroundings, right? So that is what the basics of science of thermodynamics, right? Yes. So this is about process number 2 to 3. So the process number 2 to 3, how it works? See, listen here. So the process number 2 to 3, insulation at the cylinder head. So once the power is transferred to the working substance, now the insulation at the cylinder head, then the temperature drops from TH to TL. So obviously during the power stroke the temperature remains constant, we have assumed, right? But in the real case also it won't be there, right? But with respect to this transfer of heat energy to the working substance, after that the gas get expanded, right? The working substance get expanded. So how it is expanding? During expansion process the volume get increases, right, and the pressure and temperature get drops. That is what TH to TL, right? So this is what the low temperature we reach during the expansion process, right? And the gas expands and does the work. What is that work? Actually mechanical work we can able to consider. The piston is connected with the connecting rod, and after that we are having crankshaft, it is connected to the wheel. So I can able to convert that as a work, right? And the process is therefore reversible and adiabatic. So this is the ideal process we can able to consider. Okay, now. So why? Because Q equal to 0 we have assumed. So Q equal to 0 in the sense, so it is in the practical case actually it is not applicable, right? Now the third process comes to the third process. reversible isothermal compression once the expansion process done actually, right? Okay, na? So there actually we are having because of that expansion the TL we reaches, right? And then after the TL reaches reversible isothermal compression, right? So with respect to the TL, same TL, I need to compress the working substance, right? So that the delta T will be minimized. So if the delta T will be minimized, then the heat rejection will be minimized actually, so that the performance will be maximum. So that is what actually we have assumed with respect to this ideal conditions, right? But in actual cases, we can't able to maintain that as TL, right? Because of the friction during the compression process, the temperature slightly get increases. So TL to some other value, right? But it is greater than the TL, right? But if I do in this way, actually, I can able to minimize the heat rejections, so that, right, I can able to maximize the efficiency. In that way, I supposed to assume with respect to the ideal condition. So that is what the reversible isothermal compression. Here the TC equal to constant. What is the TC? TL, right? So TL of 3 equal to TL of 4. So remains constant, right? So up to this process, actually, we can able to compress, do the compression process. Okay, na? Right. So from this actually, we assumed as with respect to the energy is transferred to the sink with respect to the QL, right? Okay, na? So what is that actually? Some amount of, because of the sign of thermodynamics, some amount of energy has to be transferred to this. So that is actually I maintained with respect to the same temperature. How we consider with respect to the TH, right? Energy, that is what supplied. Here it is energy is transferring to the sink, right? Yes. See, so the detailed descriptions about this this process, 3 to 4 process, insulation removed exactly with respect to the cylinder head. In that way, we supposed to assume, and TL is remains constant, so that I can able to minimize the heat rejection to the sink, right? Obviously, with respect to the sign of thermodynamics, we are surrounded by this medium, right? So obviously, some amount of energy has to be transferred to the medium, but in which way we can able to minimize with respect to the ideal conditions? So I can able to maintain the TL is constant, and again infinitely very small heat transfer to the sink at TL, right? So very small amount of heat transfer only transfer to the sink with respect to the temperature TL, right? The temperature difference never exceeds that delta T again with respect to the same conditions we have assumed for the source, or we can say heat supply, right? So the total transfer is nothing but QL. So if I maintain this as very less TL, so I can able to minimize the QL losses, heat rejections, right? And similarly, if I maintain that same TH, I can able to maximize QH in the 1 to 2 process I'm telling, right? So that I can able to increase the efficiency for the ideal cases, right? Yes. Now come to the after that real compression actually we are having. So that is what the exhaust actually we discussed, and after that compression is nothing but, now it is well insulated, right? So assume that both the valves are closed actually, we can able to assume. Now it compressed 4 to 1 actually. What is that 4 to 1? Again it reaches the TDC, right? It reaches the initial state, right? Initial process, initial state it reaches. That is why I said this is comes under cyclic process, right? And ideal processes we have considered. So that is why ideal cycle we can able to consider, right? See, what is that reversible adiabatic? Again, Q equal to 0. I can able to assume. So I need to compress the working substance in such a way that, right, whatever the heat generated is nothing but it should not rejected to the surroundings. So for like that, I have well insulated over here, right? Yes. So for this, what are the assumptions actually we are having? What are the things we are having? Temperature rises to TL to TH, right? So until that, actually, I is supposed to compress it, and insulation put back again. That is what, and the gas is compressed in a reversible manner, right? And the temperature rises from TL to TH. Again, it reaches to the source temperature, right? So in this way, I supposed to assume the Carnot cyclic process actually. So these are the four various processes we are having. See, with respect to the PV and TS diagram, I can able to mention it. See, especially with respect to the TS diagram, what is the first process actually we have started with respect to the power stroke 1 to 2. This is for the heat addition process, right? What about the heat addition process actually? It is maintaining at the same temperature, TH equal to TH. What is the TH? 1 equal to TH2, right? Then only I can able to add more amount of heat energy to the system, right? So that is what I have considered. Okay, na? And the volume get increases. That is what the expansion process taking place. So volume get increases and pressure get drops actually. Right? Okay, na? So in that way actually we can maintain. And after that 2 to 3 is nothing but actually we call it as isentropic expansion process or reversible adiabatic expansion process. If the gases get expanded with respect to the Q equal to 0. Right? Here the Q equal to 0, it is expanded. Right? And then 3 to 4 is nothing but exhaust actually we are having because of the sink. Right? Some amount of QL is rejected. That is what heat rejection, right? We are having. And after that 4 to 1. So during the what is that actually we call it as a heat rejection. How we are rejecting the heat actually with respect to the same temperature as maintained as constant, TL3 equal to TL4, right? And because of this compression, right, slightly pressure get increased and volume get decreases. So that is why 3 to 4 it get compressed actually. And after that 4 to 1 again isentropic compression, reversible adiabatic compression. Here also Q equal to 0, so that I can able to reach the initial state. Like that we have assumed actually. So this is what the TS diagram. See, for an isentropic process is nothing but entropy remains same. So S2 equal to S3 here, and here also S1 equal to S4. So reversible adiabatic wherever we have considered, that is what isentropic. So in that way I can able to frame it, right? So this is the PV and TS diagram for the Carnot cycle. Okay, no? Yes. See, this is what actually we know that in real time actually we can't able to construct it, right? So the hypothetical engine, that is what they have mentioned. The hypothetical engine or ideal engine operates on the Carnot cycle. We know that. See, generally we know that the need of thermal or efficiency of heat engine, whatever it may be. So we know that W by QH, right? What is W? QH minus QL by QH and 1 minus QL by QH, right? See, since the Carnot engine is reversible, we can able to apply the absolute Kelvin principle over here, right? If it is absolute Kelvin principle over here, I can able to sense that the temperature heat transfer is nothing but directly proportional to the particular temperature. That is what QL by QH is nothing but is equal to TL by TH, right? This is applicable for the reversible conditions. So if I know that need of thermal or need of Carnot is equal to 1 minus TL by TH, right? This is what need of Carnot or ideal, whatever it may be, right? So this is known as the Carnot efficiency and is the highest efficiency that a heat engine can have while operating between TH and TL, right? So this TH and TL must be in the Kelvin, absolute Kelvin, I said, right? Yes. So this is what we can able to calculate the performance parameter. So the need of Carnot actually I got, right? Need of Carnot I got. What is the need of Carnot? It is proportional to 1 minus TL by TH, right? It is equal to. Now what about need of actual? Need of actual is nothing but W by QH, whatever we are having. So if I got need of actual equal to 70% and need of ideal or Carnot equal to 60%, then it is not possible, right? The given conditions is not at all possible to construct the particular devices. So for that purpose only we have framed the Carnot cycle, right? So this is the application of Carnot cycle with respect to the heat engines, right? So in the reverse way, if I consider, that is what the reversed Carnot cycle we are having, right? So that actually reversed Carnot cycle we will discuss in the next lecture. And thank you one and all. We'll see in the next lecture. Thank you.